Hello and welcome, ladies and gentlemen, to another tutorial for AI UI. This time we are going to talk about a dataset that is really present right now. It's all about COVID-19, also called coronavirus. You can find this dataset on Kaggle. Okay, I will link you this in the description. And what we got here are 5 datasets, but the most important is this one. The others are just taken out of it. And we got an index column, serial number, date, province, state, country, when was the last update, and most important, confirmed cases, deaths, and recovered cases. So I already did this project right here. I named it COVID-19. And let's have a first look at the data. So we got several similar columns like province, state, and country. We will drop the country column and we will use province, state as filter column. I will tell you what I mean with this later on. Some provinces are not filled in. That means the rows are empty. So if it was like that, I was taking the country value to fill in the province state column. Okay, I added another class called country class because if you look at the histogram of country, you see that most values come from China, and that means China is overrepresented. If we add another feature called country class with 2 values for China if it happened in China and other if it happened out of China, then we get a more evenly distribution. And also you have to imagine that China might treat the virus much harder right now than other countries in the world. So it might be a good idea to add this feature to our table because the neural net might make some advantage out of it. Next, I dropped date, country, and last update because we don't need a date column and we don't need the country column anymore. Then I was label encoding country class. We named it China and other, but these are values a neural net is not able to interpret. So to check if the encoding has worked as we wanted it to, we can take a histogram node, choose country class, proceed, and we should see the same distribution right here, but with another label. So now we got a label O and 1. The distribution is the same, 385 values for O or China and 835 for China and O and 883 for other countries. So what did I do then? As you can see here, I took a box plot to see how the values are arranged. What is the range of the actual values? You can see confirmed is ranging in between 0 and 60,000. Features like deaths is much smaller. We don't have that much death cases right now, what is really good. But for the machine learning model, this might lead to problems because it could rely more on the higher values of confirmed cases than on all the other values. And what I have to tell you is that I also added another feature called distance. Distance is just simply calculated with latitude and longitude values out of Pythagoras, just simple math. But I think this is more important to a neural network than adding several classes for the country. Okay, if you have Italy, if you have China, if you have the US, and so on. These are specific classes, okay? These are absolute. If you add a distance, you got a value that is more interpolatable, okay? That is not that absolute. It's just relative. And what is the distance? I have to tell you, it is just the distance between the source of the virus, okay, and the province or state the entry is from in this specific row, okay? So right here we are scaling in between min-max. That means the min-max scaler you can find in pre-training will take every column I gave it and scale in between a range from 0 to 1. Axis 1 stands for columns. This means it takes the minimum value and the maximum value from a specific feature, for example the distance, and scales the value in between 0 and 1. You can see this right here if you take these two box plots, one at each other. You can see that the scaling was done. Before we got a range in between 0 and 60,000 for confirmed cases, for example, and now we got all confirmed cases, like all the other features, in between 0 and 1. So let's go further to a very specific node. We call it sequentialized filtered. If you have a look at the data, see here in Excel, for every day that has been updated, you got a province and its reported values. Okay, you cannot just go on and make a time series out of it. Normally, you would take the values and create from this table, for example, with a window size of 3 and 3 features, this kind of time series. You can't do this with this data set because you got several different features under each other from one row to another, and you have to filter first, for example, for a specific state, and then you can take these values one day after another to build a sequence. You want to create a sequence from deaths recovered and distance to make some predictions into the future, okay? So that a neural net might find a way to interpret the sequence of recovered cases, of death cases, and confirmed cases to bring in relation to future cases, maybe, okay? So you have to filter first before you can sequentialize your data. This has been done here. We got 1003 examples and 50 features or 50 columns. So what now? We have to drop some columns. We sequentialized it, but we don't want to predict country, class, distance, recovered, and deaths, so we kick it out. We just want to predict confirmed cases with our model. What I have to say here is in the sequentialized filtered node, I used the window size of 10. That means we got 10 time steps, 10 days into the past to use them to predict one day into the future, for example. Okay, we exclude data, for example, that has not enough time series present. Okay, what can we take here? Maybe Italy has enough. Egypt, for example, started at 14th of February, so they just were reporting 4 values, and with a window size of 10 we cannot create a time series with window size of 10, so we kick these values out before sequencing. that means we lose data, but we cannot rely on this. So also we exclude our filter value. We filter after province state. That means it takes, as I have shown you right here, it takes a specific province and filters the values and then creates the time series. But we don't need the province value later on, so we kick it out. After kicking out the rest of the columns, I already told you, we make a train validation test split. We got these 3 data sets. Anytime you want, you can download your data sets right here as CSV data table. And yeah, I've chosen shuffle. Best way might be normal, but let's not talk about this right now. Okay, and as you can see here, I tested, or I wanted to show you some. We got here just a distance plot. Okay, I just wanted to see the feature distance, time series number 9 value distance, its distribution in this data set, in our training data set. So why this? The problem is if you got a neural network and you got 2 classes, for example, pictures of cats and pictures of dogs. If you feed 100 pictures of cats and 1000 pictures of dogs into your neural network, it will learn more what dogs might be than what a cat might be. Not only because of the lack of variation, but also because of the sheer amount of more dog images. 10 times more dog images. It's like you're learning for a test, and what you've learned most recently and what you've learned more than everything else, you might be able to do better. Okay, you can remember better, and that's the same with neural networks. So let's do some resampling here. We are oversampling. We will oversample the distance we have shown right here right now. We want a regression. We create 10 bins. That means we are binning all values, the whole distance values that are scaled in between 0 and 1, divided in 10 bins. Then we want to keep the original value, make it uniform, and now the algorithm will oversample all the values after 8 underline distance. So that leads to more values, but if we now have a look at the distribution of this, you will see it's more evenly distributed. That means all distances, so that means to all regions, other countries, are evenly represented in the data set right now. This plot might take some time longer because we got much more samples right here, over 3,300, and these have been 700. So let's have a look. Come on, don't take so long. Okay, and you can see here right now the data is much better distributed, but there are some bins where no value has been before. There will also now not be any value. Okay, so we have more evenly distributed our data, and I've already done this before. Okay, I had to make a shortcut and train again because my results were lost anyway. So what do we have here? We have shown you the architecture, the training node. We have chosen the target column 9 confirmed. We trained for 75 epochs, the batch size of 1100, shuffle through. Yeah, and we store the latest model. Right here you can see I have already done the predictions, and you can see how good the algorithm performs on several data sets. This is the test data set. The algorithm has not been trained on. This is the validation data set. The algorithm also has not been trained on, but the training process was validated with this data set. And this is the trained data set itself. You can see it fits well. Okay, so that's it, but we got one more thing to show. We've programmed a recursive prediction node. That means if you go here to interpretation, recursive prediction, you can go there, put in a data set, for example, the test data set. So you got several rows, which stand for several examples. And you can go here and choose one example. You can also import a new data set. And then you choose how many loops. And what this node is doing is it takes your trained model, puts in the inputs, and predicts the next time step, because our model is just trained on one target, and for that just one time step in the future. Okay, so it takes this prediction right here, puts it back in to the data stream, and then predicts with this already predicted value the next value. Okay, and so on. You can say, give me 20 loops. That means in our case, look 20 days into the future, and you might get a scaled number for confirmed cases into the future. Okay, you can take another example, but be aware, you make predictions upon predictions. This is clearly wrong, because confirmed cases cannot drop, because yeah, they only sum up. The value has to rise over and over again. So that's it. I hope you enjoyed it, and I hope you got some questions. Please let me know. I will try to answer whatever I can. I know this was maybe too fast, but there might be so many questions. If you got one, just ask, and I will try my best to solve your machine learning problems. Thank you.